Let's see if we can find the measures of the angles and arcs on this circle. Before we begin, I should tell you that this is a 90-degree angle. If I don't give you that, it's going to be very difficult to figure these things out. Once I give you that angle of 90 degrees, we can figure out the measure of angle AOE. If I have 40 degrees, I need another 50 degrees to finish making that 90 in the center of that circle. Angle COB, that's an angle, so COB, that's a straight angle, or a straight line really, so that's 180 degrees. So arc CE is created by going from C straight to E. That's an intercepted arc of COE, which is a central angle of 40, so that arc is also 40. Arc AE goes from A directly to E as quick as I can. That has a central angle of 50, so its intercepted arc is also 50. Which makes sense, because if the central angle of COA was 90, the 40 and 50 would make a 90-degree intercepted arc. CAB goes from point C to A to B, so all the way around the circle. That's half the circle, which is 180 degrees. But what I want you to see here is 180 degrees is half the circle. It still matches the central angle, which was COB. That's a straight angle, 180 degrees, matches the intercepted arc of 180. So the last one we need to find is arc ECB. So again, let me clear some of this markings up, but I'm going to leave the numbers. This was 40. I have to start at E, go to C, and don't stop until I get to B. Much like the angle addition postulate, I can add arcs together. If CE is 40, and from C all the way around to B is half the circle, that's 180, then ECB is going to be 40 plus that 180, which is a total of 220 degrees for that arc. And that's how we're going to find arcs and angles on circles. So let's see if we can do a proof. And I'm not going to list the steps, I'm just going to talk this one out and mark the picture. It says, given to me is that the measure of arc AB is the same as the measure of arc CD. So I'm going to mark the circle much like I mark triangles and quadrilaterals and everything else. Those are the same. I'm trying to prove, so I'll put this in a different color, that AB is the same as CD. Well, here's what I'm thinking. If I can show that those two triangles inside the picture are the same, then I'll be able to say that the two pieces are the same by CPCTC. So if you thought you were done with CPCTC, you are sadly mistaken, because we're going to need that a lot with circles. So here's how this is going to play out. If these two arcs, AB and CD, are the same, I know that the intercepted arc always matches the central angle. So those two central angles have to be the same. But I also know that in every circle, all the radii are congruent. So this radius of CO is the same as this radius of OD, which is the same as this radius of OB, which is the same as this radius of OA. And now when I look at those triangles, I have a side, angle, side, matching a side, angle, side, which tells me that triangle BOA is congruent to triangle COD. So that means that segment AB has to be congruent to segment CD because of CPCTC. That's a very useful theorem. So let's put that into words. We started with two congruent minor arcs, and we ended with two congruent chords on the circle. So when we put that into words, it looks like this. In a circle, if two minor arcs are congruent, their corresponding chords are congruent. And vice versa. If two chords are congruent, then their corresponding minor arcs are congruent. So if you look at the next two examples, it's a very simple theorem to use, and we've proven that it's always true. So if this arc right here is 70 degrees, and this minor arc over here is 70 degrees, the chord that is created by connecting the endpoints of that arc have to be the same as the other chord created by connecting the endpoints of the other congruent arc. So x in this case is 4. So 70-degree arc, 70-degree arc, 4 inches, 4 inches. So on the next circle, how would I go about finding x? Well, you wouldn't. There is one more piece of information that I have to give you. If you ever see an isosceles triangle, so I'm going to give you this. If you see an isosceles triangle inside of a circle, you've got some congruent arcs and can figure out how far around the circle you're going. Because this is a congruent arc. So congruent chord. This chord is congruent to this chord, which means this arc, x, is congruent to this arc, which we'll call x, because it's the same thing. And now I know all three pieces of the circle. I've got a piece that is x, a second piece that is congruent, and a third piece that is 100. And we know that all the arcs on a circle should add up to 360 degrees. So 360 is going to equal 2x plus 100, which means 260 will equal that 2x, which means when I divide by 2, each of those arcs must be equal to 130 degrees. And that's how we're going to use that theorem. If ABC is equilateral, well, that's nice because that's one chord congruent to another chord congruent to a third chord, which means all the minor arcs, arc AB, arc AC, and arc BC, are the same. So if I just want to know what is the measure of from arc AB, I just have to go from A to B. There's 360 degrees in that circle. Split evenly by 3 arcs is going to be 120 degrees for each of those arcs. So again, isosceles triangles, equilateral triangles, very useful in circles because of this theorem about the arcs being congruent if the chords are congruent and vice versa. Here's a less known theorem but still very useful. If a circle is in a circle, if the diameter is perpendicular to a chord, it's going to bisect the chord and both its arcs. So here's what that says. If diameter QS is perpendicular to RT, so that means I get a 90-degree angle right here. Not only did that cut the arc RT in half, so RS and ST are congruent, it also cuts the chord RT, so RV and VT are the same. And that's the information you're going to get from that theorem, if the diameter is perpendicular. So let's see how we can use that to solve some problems. As you're following along with the notes, you'll notice that some of the information isn't enough to solve the problem. That's why I want you to watch this video. In this first example, all I need to tell you is that you have a 90-degree angle right here. And at first glance, it may not seem like you're getting that much information, but you really are. From that last theorem we learned, we know that if the diameter is perpendicular, it cuts the chord and the arc in half, which means x has to be 6. And if x is 6, that means this entire chord from this point to this point is 12. Just like this chord from this point to this point is 12. And if two chords are the same, that means their minor arcs, this 100 and all of this, are the same, 100 and 100. So putting it all together, if that arc is 100, and it got cut in half into two pieces, that means this arc of y right here has to be half of that 100, or 50. And then z goes from this point to this point, so we're talking about that minor arc. Well, we already have 100 here, 100 here, but you have to be careful. There's a small sliver of an arc right here. So we can't just say that we're left with 260 for z. We need to figure out what this small arc is up here. So I'm going to look at the semicircle. If I go from this point all the way around to this point, that's 180 degrees. But the arcs that are already taken up on the semicircle are 100, so I got to get rid of that, and 50, so I have to get rid of that. Oops. 50, so I have to get rid of that. And then that's going to leave me a total of 100, I'm sorry, just 30. So this is a 30-degree arc. So now I have all the pieces I need. I've got 360 degrees minus the 100-piece arc, minus the other 100-degree arc, minus the 30-degree arc, which is going to leave me a total of 130 degrees left over for arc Z. That's a pretty complex problem, and this is going to take some practice. All right, on the next example, I need to give you the same thing. All I'm going to give you is that this is a right angle. So that diameter cut the chord in half, so I do know that x is equal to y, and it also cut the arc in half. Now right now it may not seem like that's giving you very much information, because how am I supposed to figure out x and y? When in doubt, draw yourself a radius to create a triangle. Because while we knew that the radius was 10 from point O to this point, I also know that all the radii are 10. So if I draw this triangle, I know this radius is 10, and I know this is a 90 degree. I'm looking at a right triangle with sides of 6 and 10. So this is a 6, 8, 10, which means y is 8. And we already said that x is equal to y because it was bisected, so x is also 8. Last example. Again, I need to tell you that this diameter is perpendicular to that chord. So right away we know arc was bisected, chord was bisected. So it says OZ is 12, and the measure of angle YOZ is 60 degrees. That's a 30, 60, 90 degree triangle, because if I have 90 and 60, this is a 30 degree angle right here. So A and B are the same because those two that chord was bisected into two congruent parts, and C goes from this point to this point. So I'm going to find the pieces of this 30, 60, 90 triangle. So let's just do a quick review of that. 90, 60, and 30. This part is C, this part is B, this part is 12. On a 30, 60, 90, remember that the hypotenuse is always double, the short leg is always 1, and the long leg is always root 3. So to go backwards from 12 to the short leg, I'd have to divide by 2, so that would be 6. To go from the short leg to the long leg, I have to multiply by root 3, so that would be 6 root 3. And we know that A and B are the same because it was bisected by that diameter, so A is also 6 root 3. So you see these right triangles and 30, 60, 90 triangles and all these things about equilateral isosceles are going to come back in circles and really going to push your understanding of geometry.